Modern materials are fundamentally anchored in polymers. For increasingly diverse applications, techniques in tailor designing chemical functional groups have become indispensable. But as polymer structures become increasingly complicated, so do the chemical synthesis involved. In the traditional sense, this implies additional steps, additional waste generation, and additional energy expenditure. With increasing global ecological awareness, preference is given to technological approaches that can reduce the consumption of non-renewable resources and minimize the use of generation of hazardous substances. This essentially means a shift towards the use of renewable and sustainable feedstock and environment-friendly synthetic pathways. In this research project, advanced functional materials are targeted through the marriage of these green practices. The use of natural fibers and biomass-derived monomers as sustainable feedstock, and radiation-induced graft polymerization and multi-component reactions as the environment-friendly chemical processes. The Philippines is home to a wide variety of agro-based natural fibers with desirable mechanical properties. These materials have become ideal substrates as they are sustainably cultivated. Furthermore, their lignin content has been increasingly utilized in producing green aromatic compounds for use as bio-based polymers. Functional materials derived entirely from biomass pose greater scientific, economic, and environmental contributions to society. Apart from their mechanical advantages, natural fibers are otherwise inert. Using RIGP, these inert surfaces can be transformed into functional ones by covalently attaching polymers with desired properties. This can be achieved by simply subjecting the substrate to ionizing radiation to create reactive radicals on its surface. These radicals can initiate the graft polymerization of any vinylic type monomer without requiring the use of toxic initiators or catalysts. It can be used on substrates of any form under mild conditions. The grafted polymers can be further functionalized using MCR. Conventionally, to combine 3 or more components, sequential reaction steps are implemented alongside multiple purification steps. In MCR, multiple chemical structures can be formed into one product in one facile step under mild conditions. This allows a high atom economy with reduced chemical waste generation. An example of this is the Kabachnik-Fields 3-component reaction. KF3CR can combine equimolar amounts of aldehydes, amines, and phosphites to yield alpha-aminophosphonates. And given the straightforwardness of the reaction, diverse synthetic products can be generated by a simple variation of the starting components and can even accommodate compounds bearing sterically demanding group like crown ethers. The RIGP MCR method can circumvent wasteful and hard to manufacture functional groups, easily immobilizing them onto a chosen substrate for various applications. Alpha-aminophosphonates and crown ethers have unique selectivities towards rare earths and lanthanides. These metals are highly useful in the industrial production of optical devices, semiconductors, high-performing alloys, energy-storing devices, and many more. The project aims to utilize locally available natural fibers such as pineapple and abaca and use RIGP MCR towards building a library of diverse functional materials for selective uptake and recovery of industry-valuable metals. The project is expected to generate multiple scientific publications and intellectual property applications. It will also contribute to increased utilization of local natural fibers, stimulating the country's local agriculture and textile industries.